We can start. Hello, everybody. My name is Corina Posaranu, and I am one of the co-chairs of the conference. And it is my pleasure to introduce our third invited speaker, Marsha Chechik. She is a professor and chair in the Department of Computer Science at the University of Toronto. She received her Ph.D. from the University of Maryland in 1996. Her research interests are in the application of formal methods to improve the quality of software. She has authored over 200 papers in formal methods, software specification and verification, computer safety and security, and also in requirements engineering. Marsha has been program committee co-chair of the 2021 ESEC FSE conference, the 2018 ICSI conference, the 2016 TACAS conference, and the 2016 Working Conference on Verified Software, Theories, Tools, and Experiments, also of the 2014 ASC conference and the 2008 Concur conference, the 2008 CASCON conference, the 2009 FACE conference. She is also a distinguished member of ACM and the vice chair of ACM SIGSOFT. And today she will talk about safety assurance and reliability from a software engineering perspective, a very appropriate topic for our conference. So please welcome Marsha.
Thank you so much. Thank you so much, Karina and Radu, for inviting me. As a way of disclosure, I did give a keynote address at SEFM 4 years ago in 2017 when I was just beginning to work on assurance. And my goal here is to talk about something a little bit different from the keynote address that I gave back then, as well as tell you what progress has been made in this area. So in terms of who I am and what I do, I've started working on static analysis of programs. I then worked on model checking and formal specifications. I built a program software model checker back in early 2000s. I then looked at reasoning about incomplete and inconsistent systems, runtime monitoring, modeling, specifically about variability, and then kind of broadly interested in reuse. And all of those things kind of combined got me interested in safety, and specifically safety of software-based systems, and specifically automotive systems. Now, why automotive systems? Well, they are complex. So we have this massive software complexity with millions of lines of code in cars. They are ubiquitous. Most of us need to drive. And they have very significant end user configurability. So companies need to maintain complex product lines, and building and testing an individual product is mostly infeasible. And, of course, we're also aware of the current self-driving race and the associated accidents. So very rich space with lots of problems. In terms of the autonomous driving race and failures, you probably know about the Tesla Model S autopilot fatality in 2016, and then another one in 2018 with the Uber pedestrian fatality, another one again in 2018 for Tesla for the driver fatality. And, while our goal is, of course, to try to prevent fatalities, our goal also broadly is to try to support creation of safety critical autonomous systems, so those with machine learning components that might not be quite as lethal as autonomous cars, but maybe like delivery robots and luggage robots and little Roombas that we have in our houses. All of those have some elements of being critical and having machine learning components. So the overall goal of my work is to improve safety, security, and dependability of advanced software systems. So first of all, I had the word assurance in the title. And let me talk a little bit about what that means. So assurance in general is very closely related to safety. So what we're trying to do is we're trying to determine or assure that there is no unreasonable risk of something happening incorrectly. And the risk is the product of severity and likelihood. So this safety is different from, say, safety properties that we use in verification. We're not just looking for finite counterexamples. Instead, in this safety, we're trying to determine what is a crash, what is a hazard, and then try to estimate risk of such things, and then try to build an argument as to why this risk can be avoided. Now, I mentioned the word argument. So in order to deal with issues of safety, international organizations such as ISO have come up with so-called standards to serve as documented agreements. So they contain technical specifications or other precise criteria to be used consistently as rules, guidelines, or definitions of characteristics to ensure that materials, products, processes, and services are fit for their purpose. That's all that these standards are. But concretely within the different domains, organizations are coming up with very specific, very detailed standards. So some of them, IC 62304 for medical devices, prescribe what should be the right software lifecycle processes so that software that is built with this is deemed safe. You probably are, or some of you are probably familiar with the software considerations in airborne systems. These are the things that govern a lot of our plane development. And in the world of cars, ISO 26262, the functional safety of road vehicles is the standard that is being used for all car manufacturers before the car can be certified to be on the road. If you look at the way that these processes are done, so again, the one I'm most familiar with is the one for cars. What you have is something called a V process, which means starting from hazard analysis, we then build safety concepts and then architecture, and then we do the software hardware development, and then verification and validation. So on the left side is ultimately the notion of building safety requirements. And then the thing on the bottom is this whole process is built around creating an assurance or safety case. So an assurance case or a safety case is formally reasoned, auditable artifact. So auditable as in somebody else can come and read it and convince themselves that you've done the right thing. Created for contention that its top level claim or set of claims is satisfied, including systematic argumentation and its underlying evidence and explicit assumptions that support the claim. So again, what happens in the high assurance systems is we're building a document or a model that can be reviewed by somebody that is an argument that at the end builds evidence that the particular goals in the argument have been satisfied. The evidence can come in many forms. Test results, analyses, for my interest, model checking results, but it could also be something informal like expert opinion. And the argument itself is also quite informal, at least in the particular automotive companies we work with notions of sufficient and adequate being used much more than a particular formal argument. Now, notations for creating assurance cases vary widely. General Motors, the company we work with, produces Word documents as an assurance case, but there's also been a lot of push to create more structured notations for assurance cases, and the one that is often used is goal structuring notation or GSN. And what it does is it has notions of goals, assumptions, context, strategies, justifications, etc., organized as a tree, and then the different shapes correspond to different parts of this notation. So making it somewhat more reviewable, because not only do you have a structure and a tree shape going from the upper level goal down to where evidence is, but there is also a shape that corresponds to the particular type of argument that fits, again, assumptions, context, justifications, etc. So let me give you an example. This particular example is the lane management system. Those of you who drive relatively modern cars, I recently got one of mine with the lane management system. I was very excited to actually see the system I was studying in real life. But the idea is to keep the vehicle in or near the center of the lane to avoid crashes caused by distracted driving. It is a safety critical ADAS, so Advanced Driver Assistance System, and thus it's subject to the ISO 26262 standard. It's comprised of 3 subsystems: lane keeping system, which keeps the vehicle within the lane markings, the lane centering, and the lane departure warning system, which warns the driver when the system determines unintentional lane changes. And so an assurance case, or a fragment of an assurance case for the system, and you don't need to read all of this, but basically it's a tree. It starts from the goal that says the system is safe. We have an assumption, so in this case, assume non-rainy driving conditions. Not a realistic assumption, say in Britain, as far as I understand. Then we have some sort of decomposition over safety goals. So for example, that the system will notify the driver if it fails. The triangles here mean that something is undeveloped and more information will be needed. We have a condition, so this is system hazard, failing to notify driver when the system fails, the vehicle hazard, the unintended operation of vehicle feature, etc., etc. We decomposed. What we have at the bottom are evidence. So one can be verification of software that actuates alerts. This would be a verification step. S6 is a static analysis piece. We can have a couple testing results that we can add into this overall picture. And another one that I want to bring your attention to is, in this particular case, I also have one more sub-goal, which is the pedestrian detector works correctly. Okay, now why is all of this interesting here? Why am I telling you this? So first of all, this is an argument, again, around the particular evidence that testing and analysis people like, because it combines assumptions and abstractions and many other things that we do in order to get something analyzed or tested into the broad argument to make sure we don't miss anything. And it natively combines reasoning about sort of developed systems and machine learning systems like the pedestrian detector, all in one structure. So that's sort of why I'm interested in studying assurance cases. They are natural unifiers for a whole lot of activities. But to be those unifiers, we got to solve a number of problems related to assurance cases. So first of all, they are informal, and they really cannot fully be made formal because they are complex and they are related to existing engineering practices. And we now have a rapidly emerging machine learning in development, which challenges a lot of assumptions that are being made in standard engineered processes. So that's what we try to study. So in terms of my interests over the past few years in this space, we have been studying various issues related to the argument with the goal of trying to make those arguments more rigorous and therefore provide analysis and in the future, notions of repair and synthesis, because if you know what you're looking for, you can help, as well as broadly facilitate reuse. So one of the problems that often happens in realistic systems, at least in General Motors, every change in the system requires rebuilding of an assurance argument, which means stability of assurance and being able to see how much of assurance argument needs to be redone is a very big problem. Historically, I've been coming from the evidence space, so development of methods for evidence generation, composition, and reuse has been an ongoing interest, but I'm not going to talk about it in this talk. And recently, we've started doing some support for machine learning argumentation for development of assurance requirements and evidence and assurance case templates. And the focus of my work has been on reliability. So I'm hoping to talk a bit about this. Okay, argument. Well, let's leave the lane management system behind and talk about something smaller and cuter. So this is the floor cleaning system, which is designed to clean and vacuum a floor. The floor can be grimy or contain objects, and the objective is to vacuum the floor if it contains objects and clean the floor if it is grimy. Let's not worry whether this is safety critical or not. This is intended to be a simple example. So in general, the hazard in this space is if I'm trying to clean a tile while it contains an object, so like my rubber boots, may damage the system and cause unsafe behavior. So I'm going to try to build an assurance case for such a system. So my claim is the system never becomes damaged. I have a strategy, which will be an argument over subsystems of my floor cleaning. One of the claims will be that the cleaning system never caused the floor cleaning to become damaged. And the second one is the vacuuming never caused it to become damaged. So I'm just going to kind of decompose like this. And by the time that I'm done, I'm going to have myself a safety argument. Wait, you say, why is it even appropriate to decompose over individual systems? Like, why is this strategy valid? Two, maybe I missed some cases. Were there maybe interactions between the subsystems? Are all of the subsystems included in the decomposition? And maybe there are all sorts of other argument fallacies. So, me trying to build a tree doesn't necessarily mean that this corresponds to any reasoning. So this case is too informal, and we may want to formalize. And if we do, we can manage to automate reasoning and help find a variety of bugs. So that's what we've been doing in this space in a couple papers, starting from SafeComp 20, with the goal of formalizing core assurance case concepts, and then categorize decomposition strategies by their properties, and then identify conditions under which these strategies are deductive, as in they can be following a proper logical reasoning. And if so, we can generate deductive strategies. And in fact, you can then have theory improving support that goes behind the scenes and then help check that you're doing what you're trying to do. So the formal claims are things like what is an execution and what is a property and what is a claim. And so an example can be that a vehicle never overheats when operating under a particular speed under 120 kilometers an hour, where the system would be a vehicle and a property would be that the system doesn't overheat. And then you have the execution set, which is all the instances of the operation. And so with these formal things, we can create much more formal decompositions. So for the floor cleaning system, I would have a decomposition over different domains, or domain decomposition over tile types. So something which is clean or grimy, which is just clean, which is just grimy, and then a completeness claim that says I've covered all the possible types. So this looks relatively benign. Formally, it looks a little uglier, but with familiar logical notation. Another decomposition template can be about properties, where we are trying to decompose a particular property over a property set with the justification that this property set is complete. So our decomposition is valid. Or even do things related to support for mathematical induction. So if I do a step, then my inductive step remains valid. So if I do such things, then of course I can take strategies and formalize them in a theory improver, and then have support for validating the assurance case. And so that is exactly what we were doing, using Lean as a theory improver to encode correctness of strategies. And this way, the assurance case gets translated into a theory improving argument. And therefore, with a theory improver underneath, we can locate potential bugs in the overall process. So the system that we built starts with encoding of strategies and encoding of system models. And then there is the automated proof template, using a theorem prover and a number of tactic scripts that then allow, as we are analyzing the assurance case, either produce debugging information or produce a tactic script, which is an argument that can be reviewed, that says that the overall assurance case is valid. And so the paper that we put in the proceedings of SEFM this year talks exactly about this automation. So the way that this would look for the floor cleaning system is we start with a global goal. And then, so this was our original parent claim. And then we would have an argument by lien formalization. So for example, the property damaged is not reached, which is formalized in lien using property patterns as absent globally damaged. And then we say that the property is correct and the decomposition is valid. And so what this builds is both the formalized strategy, which is, this is correct, the decomposition is valid, these are my two property decompositions. And then I also have parts of the argument about the formalization itself, which are stored as theorem proving tactic. Right, so this is all exciting. Now, who would ever want to do such a thing? This seems heavy-handed and likely not usable in the generic context. Well, on one hand, yes, that is true. On the other hand, having the underlying support allows us to do a variety of things with assurance cases, specifically things related to reuse. And those things can be lighter weight or heavier weight, depending on how much formalization the assurance case allows. So what I want to do is talk very, very briefly about what are some of the activities one can do with reuse of an assurance case. So we've looked at reuse on 3 different levels. One is if I have a system and the system is changed, how much of the assurance arguments can be preserved and which ones would need to be redone? The second argument is if I have a change in one component, to what degree would this change affect other components and therefore their associated arguments? And what can be some of the ways of thinking about assurance compositionally? So let me talk a bit about this. So in the change impact assessment, the story is basically the following. I have a system model, and that system model has a safety case. And that safety case is obviously related somehow to the system model. Now the model is undergoing change, becoming, well, a different one, so a prime. And what I now want to know is how close the new safety case is to the one I started with. Okay. So the way that we're doing this is through impact assessment to identify how changes in the system end up affecting the safety case. So at a relatively lightweight relationship between the system and the safety case, and again, sorry for a pretty involved slide, assurance cases are clunky and take a lot of space. So this particular one is something back in the automotive domain. And I'm using a cryptic thing called ASIL, and ASIL stands for Automotive Safety Integrity Level. And so this particular case is the assurance, is the outcome of the change impact assessment on a particular assurance case that we built. And in this case, this is the opening a door when the car is already moving. So this is one of those things that, like in a van, you can press a button and open a door. And if the car is moving too fast, that button should not activate the door opening because somebody may fall out of the car. And so this is the assurance case that is trying to avoid activating the actuator when the vehicle speed is greater than 15 kilometers an hour. The important part is that the outcome of impact assessment would end up saying basically the following. Things which are green can stay without a change. Things which are red are wrong and need to be redone. And things with the with this circular arrow means these are reusable. We expect them to stay the same, but they may require another review. And the reason why we say they may require another review is, of course, not everything is traced to everything. And so we're concerned that we may end up missing some dependencies. And so we've been working on this whole change impact assessment in the connections between models and assurance cases for a while. So there are several papers in this space, including most recently lifting this whole process to when assurance cases correspond to product lines rather than just individual products. Okay, another one where, again, I only tell you the outcome, but not the technique itself, is a line of work related to proving that a change to one component doesn't affect others. This one is on the level of code, and we start with a system, which we're going to call a client, and a library, or all sorts of other underlying components that are used by this client. What we have been developing over the past couple of years is a program analysis method called CLEVER, which stands for Client-Specific Equivalence Checking. And the question we're trying to ask is, will an update to something which we refer to as the library, will that affect the client? And so if it is impacted, we're going to get a counterexample that shows the impact on the client. So this is why the upgrade is no longer preserving behavior of the system. And if it is unimpacted, then we produce a proof or a reason for equivalence, which can be used as evidence in assurance. So in this case, I have a little client that uses the composite library. There are two versions of it. One is called composite old and one is called composite new. And those are not functionally equivalent, as you can all check. The old version counts the factors for input num, and that version returns 1 if and only if num is composite, so meaning non-prime. But the way that the client uses this library is by comparing its return against 0. Okay, and interestingly, both versions of this library, even though they're clearly not the same, will both return 0 if num is prime and non-zero if num is non-prime. So with respect to this usage, these two libraries are equivalent. So using the library as composite j is not equal to 0 is the reason for client-specific equivalence. So, and that's kind of the idea relating CLEVER to assurance. So if the client is not impacted by the upgrade, that means all existing evidence involving the client can be directly reused, and all the arguments related to the client can be directly reused. But if the client is affected in specific ways, then we can determine conditions under which the evidence can be reused and where it needs to be upgraded. Again, sorry, I'm going through this fast. I'm actually trying to get to newer things that look somewhat different, and hoping to spend a bit more time on this. Okay, the final piece of reuse is related to trying to develop assurance compositionally. So the broad idea is I have multiple components, and each one of them comes with its own assurance case. I somehow would like to combine the reasoning that I have about each of the components over some argument over these components to be able to determine that the overall system is safe from some hazard. This broad notion of compositionality is deeply sort of beautiful for computer scientists who love to think in boxes and then combine boxes. And unfortunately, compositionality is notoriously evading safety. The reason is as multiple parts get put together, we are getting feature interactions. So whatever worked under one, when the system was standalone, when you add others, stop working so well. And you also get emergent behaviors, namely behaviors that the overall system exhibits that none of the components exhibits. And in general, the number of potentially hazardous interactions end up growing rapidly. This problem has been broadly studied by a number of people without very positive outcomes. So what we've been trying to do here is, rather than saying, okay, we can never argue compositionally, what we're trying to do is we're trying to find particular contexts in which compositionality may be possible. And so that investigation brought us to reasoning about publish and subscribe architecture with highly decoupled components and dependencies on topics rather than processes. And so what we have been doing recently, and I'm not going to quite bore you with results just yet, will only indicate that this is work in progress, is A, looking for instances where compositional verification can happen in this space, and then B, packaging potential compositional verification into formal arguments where reasoning about one component can end up being reused in reasoning over the overall system. So if all goes well, a paper on that should be available for you to read in a couple of months. Okay, so that was a very whirlwind run over arguments. What I want to spend the rest of my time on is to reason about machine learning and assurance. So first of all, in general, we love creating systems with machine learning components because machine learning is appealing by its ability to learn and generalize beyond training data. And it helps us make sense of unstructured data. And therefore, it is particularly suitable to open context systems, of which there are a lot in automotive, specifically things related to perception, where we're trying to identify objects, which we then analyze to determine behavior of the system. However, these requirements are inherently uncertain. So we're not really even sure whether something is a vehicle. The learned concepts are hard to understand by humans. So the notion of understandability remains a problem. We all have heard of adversarial examples, so small perturbations in the input space, which completely confuse the system. They're also sensitive to changes in training data. And in general, while there's active work, the verification methods for learned functions are limited to pretty small neural nets. Although, of course, there is an ongoing list of effective techniques within testing and verification in this space. So what we're doing in this space is related to reliability. Okay, so reliability is the ability of the software to function under the given conditions. And the idea that we're gonna try to do is, first, we're gonna try to create reliability specifications. So those are specifications for a realistic range of environmental changes, rather than adversarial. We're trying to develop a method for generating reliability satisfaction evidence, and then a method for reliability assurance case creation. And here we focus on components for computer vision, and we call them MVC. So lots of related work in general on reliability of such things. So people specify expected behavior indirectly by specifying a set of quality characteristics for training data sets, such as size, diversity of data, better coverage of rare events, better quality of annotations. And some others propose high-level requirements. For example, object detection component shall perform as required in all situations that ego may encounter within the defined ODD. So this is the design, the driving environment. Yet such requirements are not really machine verifiable and thus cannot be used to generate evidence. Some other work is specifically looking at reliability against image degradations that include adversarial examples where the range of degradation is imperceptible, and metamorphic testing, which does not focus on defining the range, but checks whether the component is reliable against all possible ranges of the type of image degradation considered. Whereas again, what we're trying to do is we're trying to focus on realistic changes in real world deployment. And actually, the way we're going to do this is by using human performance as a baseline. So the idea is if changes do not affect humans, then it shouldn't affect the components either. So what I'm about to tell you is from the upcoming ICSE22 paper. So the specifications identify a class of safety-related image transformations, simulating realistic changes. And we're trying to specify two reliability requirements with parameters representing human performance. So first of all, I told you that we're looking at realistic changes. So where did we get them from? We start from something called CV-HAZOP or CV-HAZOP checklist, which is a checklist with difficult and performance decreasing situations that are systematically identified for the computer vision domain. The checklist includes a perception pipeline, light sources, medium, object, observer, and algorithm that contains locations where hazards can happen and how the information is passed between them. For each location, the checklist collects a list of entries describing possible hazards. For example, a CV-HAZOP entry 184 describes reducing the transparency of the medium, which means making the medium optically thicker and thus leading to a decrease in contrast. Okay, we say that an image transformation is safety related if it can produce a negative impact on this pipeline locations. So here are some of the commonly used safety related transformations. Contrast adjustment can reduce lighting in the scene, which can cause machine vision errors and subsequent system failures. Okay, so here's the original image. Here is the contrast. As you can tell, you have a harder time being able to identify a car on this image. Now, what does it mean harder to identify? So for this, we kind of needed a metric, which we borrowed from prior work, and the metric is called image quality assessment metric. So basically, the transformations have different visual effects in different parameter domains. For example, parameter domains for Gaussian blur and Gaussian noise include kernel size and another thing called mu. The transformations also have different visual effects. So making an already bright image brighter will make the objects harder to see, but making a dark image brighter make the objects easier to see. So like how much, what should we be measuring? So this generic metric to measure visual changes is, well, we defined to be delta V, which comes from 1 minus IQA values. And IQA is the image quality assessment metric that has been studied elsewhere in this space. Let's look at examples instead. So here we have a car. This is the original image. The IQA value is 1 and the change is 0. So that's our delta V. Here are some minimal changes. The IQA metric says, yes, this is close to 1. And we're saying, yeah, small change. Here, clearly the change is bigger. And our metric says 0.71. And this one, the change is actually unreasonable. So here we're adding frosting, and our windshield is so frosted that finding a car here is just simply not going to happen. And this is a massive change, so 0.96. So therefore, this kind of corresponds to our intuition. Now, how much is too much change? Well, for that, we're going to try to ask humans. Okay, so how do we know when we should stop expecting that the machine learning component does the right thing? So what we have done is we have we have conducted experiments with human participants on Mechanical Turk. We have given them original and transformed images after we applied all these safety critical transformations. And we gave them a forced choice image categorization task, where they're presented with images with the transformation applied for 200 milliseconds. And then they were asked to choose, forced choice, one of two categories. Either it's a car or it isn't a car. And between the images, we gave them a noise mask to make sure that there is no feedback influence in the brain. And so we did this for 2,000 human participants on 8 safety critical transformations: RGB, contrast, blur, brightness, frost, color jitter, JPEG compression, and Gaussian noise. So the one that I keep on referring to is frost. And so with this, we obtained the thresholds after which the humans can no longer identify the car with appropriate confidence. And so we're going to use these things, these thresholds, in order to define requirements, reliability requirements. And they go as follows. The first reliability requirement is from the correctness preservation class. So intuitively, for a range of changes in images that do not affect human performance, correctness of the machine vision component should not be affected either. So we're given a transformation that we are applying to the images. The threshold, that's the same one that we measured with human participants. Performance metric, which measures correctness compared to ground truth, and we need ground truth here. And then the requirement is that the MVC under validation is required to have consistent M value for image transformed with visual changes below this threshold. So here we do need ground truth to measure correctness. Now, of course, ground truth isn't always available. So for this, we have one more reliability requirement. So this is the prediction preservation. And this one says, for the range of changes in images that do not affect human predictions, the predictions should stay unaffected as well. So again, given a transformation, given a threshold that we measured with human participants, and the prediction similarity metric that compares outputs in both original and transformed images, the statement is that the MVC under validation is required to have consistent S value, this metric, for images transformed with visual changes below this threshold. And notice that here we do not need ground truth. We do get some funny results with this, but we don't need ground truth. And the metric should be defined according to the type of MVC. So for example, for image classification, this can be 0 if both labels are the same and 1 otherwise. Okay, so if I look at the two reliability requirement classes, they are not comparable. The correctness preservation checks for correctness, requires ground truth. And if we satisfy only the correctness preservation, it may correctly recognize different objects before and after transformation. For prediction preservation, we don't need a ground truth, so this can be checked on unlabeled images, but the MLC may preserve incorrect decisions and change correct ones. So neither requirement is ideal and neither subsumes each other. Ideally, we would want both. So to instantiate this for the transformation called artificial frost addition, the correctness preservation will say that the recognition accuracy should not decrease if the visual changes in images are within the range below 0.84. And for prediction preservation, we would say that the percentage of labels that our system can preserve after adding frost should not decrease if visual changes in the images are within the range below 0.91. So basically, for the first 3 pictures, we expect this to work. For the last picture, we don't expect it to work. Okay, this is out of range. Now, once we can instantiate the requirements, we would also like to generate reliability satisfaction evidence, and we do this via testing. So to determine whether an MVC satisfies our requirements, we generate test cases by transforming images within the specified ranges of thresholds that we found by uniformly sampling the parameter domain, and then executing the test cases on our system. So in this case, originally my system said that this is not a car. incorrectly, but it still said it was not a car. And then I got a bunch of images where the labeling was car, car, not car, not car. What do I do with this in terms of my reliability? Well, so blue was correctness preservation. So in this example, the original ground truth is a car, and M is chosen to be the recognition accuracy. So originally, we got this wrong, but we can see here that 2 out of the 5 generated transformed images passed and 3 failed. And so therefore, M for the generated test cases is 2/5 or 40%. And originally, it was 0 because we got it wrong. And for the prediction preservation, we're trying to get the same prediction. So this is orange. So here we do not need ground truth. S is chosen to be the percentage of labels preserved from the label of the original images. And 3 out of 5 transformed images here have the same output label as the original image. This one, and this one, right? Not car. And that is what we're hoping to preserve. So therefore, the so S for generated test cases is 3/5 or 60%. Okay, so now we got some test cases. What are we gonna now do with this? Well, we're gonna accept this if values of the metric on transformed images are close enough to values of the metric of the original. Again, pardon the relatively silly example here. It is for illustration purposes. So to summarize here, there are two classes of reliability requirements. And we are trying to instantiate them using human thresholds. And then we can generate test images with visual changes below these thresholds. And then we decide that requirements are satisfied if the confidence of satisfaction is above some threshold, say 95%. Now, what does any of this have to do with assurance? Well, people have been studying, including some present company, including Radu's group, have been studying creation of assurance cases for systems with machine learning components, and specifically trying to build assurance cases with machine learning data. So this is one of the pictures from that. So here the subclaims cover all parts of the ML lifecycle. Now, the blue, so the robustness safety requirements, is where a lot of the reliability stuff that we're working on would end up fitting into this overall structure. So if we are to add reliability, we say, okay, fine, robustness safety requirements are satisfied. We will now continue building this as saying, okay, we have a couple preservation requirements, correctness preservation and prediction preservation, perhaps others as well. And for those, we will be building particular arguments. So the arguments would basically go as follows. For the prediction preservation, I have prediction preservation requirement is satisfied under the operating environment specified in ODD. So ODD is this operational design domain in which you're expected to be working. We have assumptions that the vision task is known, and the prediction similarity metric that compares MVC output on both original and transformed images are known. We now have an argument over different classes of image transformations, simulating hazardous changes in the operating conditions. And the justification for choice of those is CV-HAZOP, with examples such as contrast change, noise, weather, etc. We're then arguing over every transformation class. And so the MVC under validation is required to have consistent S value for images transformed with visual changes below the threshold that we're going to find, with justification that this comes from, it's either measured or estimated threshold of changes that do not affect humans. And we're then trying to say that this requirement is satisfied using the test data, and then show that the test data results are, so show that the S value has not decreased after transformation with a particular confidence. So the big orange things are the things where we have been developing techniques. And the rest of this is just the overall structure. The structure for correctness preservation is very similar. The red things show the differences. So here, rather than studying the metric that compares original input and transformed input, here we use a different metric which measures correctness compared to ground truth. Here we will need ground truth. But the rest of this, subject to the same metric, is very, very similar. Again, we're trying to determine that the MVC under validation is required to have consistent metric for the images transformed with visual changes below the threshold. And then we're generating test data for this, putting this within the overall correctness preservation pattern. Okay, with this, some questions to ponder. Can this approach be even applicable beyond image classification models that we have been doing for something slightly more realistic, like the actual driving scenarios? We've been using human experiments, and they are expensive. So is there anything we can do to reduce the cost by reusing experiments for a broader range of transformations? We would like to find ways of actually improving reliability using these requirements, not just saying satisfied, not satisfied. And we are also interested in trying to automate some of the assurance case construction. So, by the way of summary, we think that it's time to take safety of software systems seriously, and the assurance cases systematically decompose arguments until explicit evidence can be generated is a very nice unifier for a whole lot of activities that we do in the SEFM community. And so the way that we can broadly think about this is various support for the argument. And I've mentioned a few of the pieces related to this for enabling rigor, providing analysis, and facilitating reuse. Of course, all the things we're doing for generating evidence fit right in. There is increasing work on support for machine learning in assurance. And we've been focusing on reliability in this space. So in terms of the outlook on the future, in general, assurance case creation is expensive, whichever way you slice it. And so looking for NLP methods for building safety cases, at least from Word documents that our industrial partner is producing, and facilitate traceability between the model that we're building and assurance for the model are going to be very, very useful. The broad work on arguments related to understandability, compositionality, and debugging and repair are definitely of use in this space, because again, these arguments become the essential output of both creation and then validation of systems before let's say cars can go on the road. Anything related to generation, composition, and reuse of evidence is an obvious one. And then in the world of ML safety, we're interested in reliability of complete driving scenarios, as well as other forms of safety, as well as generation of reviewable assurance cases in this space. Okay, and the big thanks to members of my group and various collaborators that this work has been based on. Mostly in Toronto, but also in Waterloo, McMaster, General Motors, etc. So big thanks to these people. Okay, I am, I think, only 3 minutes over. Thank you, and I'm happy to take questions.
Thank you very much for an excellent talk. I'm sure we'll have many questions. And
thank you again. I have covered more ground and faster than I think should have happened. So maybe there are no questions at all, but maybe there are.
Okay, so if you have questions, you can either type them in chat or just please unmute yourselves and ask your question.
I certainly have questions.
Okay, Radu, you can start. I also have some questions.
I was being polite, allowing maybe others to ask. But one question that I have, Marsha, refers to the very interesting part at the end of your presentation on machine learning verification of reliability. One of the techniques you propose requires a ground truth, but in some of our applications, we find that the ground truth is hard to get your hands on, even if you use Amazon Mechanical Turk, and that's, for instance, in the tasks to do with analysis of medical images, where doctors cannot agree actually on diagnosis. What do you think would be the solution there?
So I don't have a solution. I mean, we got into reliability specifically because I was trying to figure out how to reason in the absence of ground truth. Okay, and we originally started by saying, well, what does reliability mean? Whatever you did before, if you've applied a reasonable transformation, you should still be able to do. You don't need to know what it is. You just need to do the same thing. And so our whole class of prediction preservation is exactly that. Don't need ground truth. As long as you predict the same thing, you're good to go. Now, we've also observed that our systems predict the same wrong thing. So we're reliable, just wrong. So that's why, again, if ground truth is available, we have another class that allows you to check against preservation of wrong results. But I'm sorry, I think that the problem of obtaining ground truth is not solvable by any of this. We can just continue reliability in the absence of ground truth. So again, we can be reliably incorrect.
So I also, actually, I wanted to, I have two questions. So one, it seems to me that what you mean by reliability is what people also call robustness, or maybe invariance to transformations. So what would be the difference, or are they the same, or?
Right, okay, two differences. One is I actually don't, so one is what are the transformations? So the particular place where we focused was not small perturbations that should mean small changes in the model, which is sort of the typical notion of robustness. We are here looking at a broad class of realistic transformations, and actually, have been looking at are these transformations bigger than the ones that have been studied in the robustness space? And yes, they are somewhat different and much broader. And second, it's not quite an invariant. We're actually relaxing this pretty significantly. That what we're trying to do is to say, A, what are the realistic changes? 2, how much of a change is too much of a change? And 3, how non-invariant you could be to still be okay. Okay, the broad thinking is the same. This is, of course, a form of robustness, but it's robustness subject to, again, a broad thing, but limited and trying to put a boundary for how much change is too much change and how close to expect.
Mm-hmm. So actually, there is, as far as I know, a growing interest even in the, let's say, robustness literature to look at natural perturbations. And in fact, yeah, Radu and myself have a recent paper on that. So maybe we can discuss online.
We absolutely should discuss.
We can even collaborate, hopefully, or.
Because one of the things which would be very interesting is an explicit comparison of techniques over the same questions.
Yeah, that would be great.
Right, because all of our comparisons with prior work was we're asking our questions to the work that asked different questions. And so the fact that, we're showing some graphs, this is unfair, right? They didn't ask the same questions. Yes, but it would be phenomenal to try to collaborate on this.
Yeah, that would be great. So the second question actually was related to, again, to the last part, which of course is very exciting. So basically, you said you use testing to evaluate the two properties that you define. So I was wondering if coverage plays a role and how it would fit in a safety case. I mean, if you do testing, do you also need a measure of how good the testing was, what kind of coverage it achieved?
You do.
Yeah, so, okay.
And what we have done is pretty naive, to be honest. We've just done uniform sampling over the space. And at least in the paper, in the ICSI paper, which is really the first published work here, this is, step zero in all of this. It would just be unfair to say that we know that we've looked at this in any significant way, because really the rationale was to try to argue that these are the right reliability requirements. Testing was, a piece in the story. If we try to look at how to do testing subject to these requirements, what is the adequate testing, what is the adequate coverage, what is the adequate confidence, all of this is completely unexplored. So brand new area poised for new work. Again,
Okay.
We'd love to collaborate on that.
Thank you. So there is also a question from the audience. So please unmute yourself, Jenna.
Okay. Marsha,
Hello.
very nice talk. Hello, darling. How are you?
Very good.
Nice to see you. Very nice work, and congratulations for your ICSI paper. Wow, 2,000 people. It's really quite strong arguments to not to accept it. But anyway, I was curious about the issue you mentioned about compositionality. And I was thinking of instead of wondering, because I mean, of course, it's very cross-cutting concern and the safety at that level. So I was thinking, instead of thinking about the compositionality level, which is really hard to consider that in this assurance case scenario, to think about more in terms of the property specification that you want to verify, so that you can kind of raise, let's say, the abstraction, how you see the assurance case as a whole. If I express myself correctly, right? So, because then you're thinking about reliability, and then you think about how do you make this, you were able to compositionally reason about, let's say, the property of interest in terms of those fine-grained elements in your model, right?
Not exactly sure that I understand the question. I'm going to try to restate, and you're going to tell me where I got it wrong.
Yeah, okay? Good.
So first of all, I got into assurance because I thought, well, I mean, I understand verification. This should be easy, right? Verification is evidence for assurance. Just stick it in and you're done. And, I came to GM and said, tell me your properties and I'm just going to assure them. And I'm like, you got to be kidding me. What we have is a very heavily guarded list of, 400 or 4 million accidents that our cars have gotten into over the history of our company. Hazard analysis, which is all of this starts with, is not interested in creating a property. It's trying to talk about avoidance or mitigation, adequate mitigation of a hazard. Okay, so all of our stuff, all of our properties, if they appear down, 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 right? So the one thing we have already learned pretty clearly, that full compositionality of assurance cases, as in take the full assurance case, take it out of the box, take another assurance case out of the box, wave your arms, and here you have a combined one, is just not going to happen ever. But what you can do is you can imagine sort of construction for compositionality, where the high-level assurance case and the high-level decomposition is such that you can do some of the pieces by the time you get to properties, by the time you get to being actually able to verify compositionally. Then you can try to compose your evidence compositionally and take only those parts and kind of fit them into the big argument. That's pretty much at best where we're going to try to get to. That you kind of have to design for compositionality. It's not going to happen on its own.
Yeah, okay. So
the particular architecture may explicitly disallow particular safety interactions or particular feature interactions.
Okay.
And so that would be the big argument that would allow assurance.
Yeah, because the thing is, in the way that Corina mentioned about how you see reliability versus robustness, that seems to me that way, right? Because I see, and you well presented that way, right? Reliability as a property, while robustness as as let's say a way to make concrete the reliability that you want to achieve the reliability, right? So I was wondering if you, for example, think about other properties that you have of interest, and then you need to decompose it into the level that you need to come into your let's say fine-grained elements. So that how would you be able to do this? Because it's kind of, as I mentioned, like it's very cross-cutting the way that you see this representation. It'd be hard to extend it to other property representations. But very nice work. Thank you, Marsha.
Thank you. So once you decompose, we can check that you decomposed correctly. Once you partially decompose, we can't yet, but it's not complicated, to synthesize a missing piece. Once you decompose, we can check for redundancy, whatever. Right? Once you go from English to math, the rest is just math, right? You can do stuff with it. You can check for missing, you can check this, you can synthesize, you can repair, you can do all those other things. This transition from very generic Word document to even words in shapes to something that a theorem prover can analyze is quite a transition. And that is really most difficult.
Thank you very much, Marsha.
Thank you. I think we have time for one last question. So Grisel Vasquez Flores had a question. Please unmute yourself.
Yes, thank you for the talk. It was very interesting. And I think you more or less answered my question with your last comment, but I was wondering, how would you handle a big set of assurance requirements, and how do you know if the decomposition covers all critical cases?
Okay, so thank you. This is a good question. So in practice, we end up building a brand new assurance case for each assurance requirement. If you know what some of those are, you can try to unify multiple of these requirements and then end up decomposing later rather than from the top level. But that hugely depends what the requirements are. So again, either you kind of design this that sort of the way that I showed in the example, where you could do this reliability and this reliability and this reliability, and this is somewhere deep inside the assurance case. But if the requirement is something completely different, then none of this assurance case is relevant. You would need to go and from scratch build a completely different one. So, so really your answer is it depends. For some, by doing the end somewhere deep inside, for some others is creating and ending brand new assurance cases. So in practice, at least in big companies, for each of the hazards, or for each of the hazard classes, they often end up building a completely different assurance case.
So it's like an iterative process, I would say.
Is it an iterative process? Again, in practice, in real companies, they kind of reuse a high-level assurance case and then end up instantiating it for a particular piece of software, for a particular maker and model. So they don't build it from scratch. They end up reusing 3/4 of the tree. They don't think of it as a tree, but still a tree, and then only start customizing down. Okay, but in again real automotive world, one of the things which is coming, and maybe already came in Europe, but is coming in North America, is the over-the-air updates of software. So basically, you have a car, it has infotainment, the software for this particular infotainment got better. What you can do is you can upgrade your kind of firmware if you want, which is not firmware, it's really all software, over the air. So meaning without going to the, but without changing the car, really, either to the dealer or even through your app. You can imagine the broad levels of safety and security that are associated with this. But of course, one of the very significant issues is Back in the old days, a car had wheels and like brakes, and they were in hardware, and so they didn't talk to each other. In a modern car, with everything is on a bus, the interactions between components are arbitrary. And so figuring out how a particular upgrade of your radio or of your GPS visualizer, what kind of impact this is going to have on the brakes or the engine is a little bit of anybody's guess. So this notion of figuring out how to do incremental certification or how to do delta certification. So you kind of do a piece and you're only trying to see how to walk that change through the assurance case. And what are you going to do in the world of thousands of possible products, so different car configurations on the road, really millions, where you cannot test everything ahead of time. I'm not immediately clear exactly how the over-the-air updates and assurance is going to go, but we are proposing some projects in this space.
Very interesting answer. So thank you.
Okay, great. Thank you very much. Thank you again, Marsha, for a talk that was really very interesting. And thank you, the participants, for the interesting questions. And I think this concludes your talk. Let me send the virtual applause. I hope you see that. And
thank you so much for inviting me. I actually really enjoyed preparing this talk, and I think that the questions have been phenomenal. Thank you.